And here's another great application of how we use the sine, the cosine, and the tangent to find angles and sides. In this case, we're going to find the conversion from polar coordinates to rectangular coordinates back and forth. So for example, let's say that we have a circle. The circle has radius r. In this case, we're going to let r equals 1 unit. So that's also called a unit circle. It's something that we'll talk about later in more detail. And let's say that we have an angle of 40 degrees in reference to the x-axis. And we want to know what the equivalent coordinates are in the Cartesian coordinate system or rectangular coordinate system. So if we express the point right there in terms of r and theta, the radius of the circle, and the angle with respect to the x-axis, we would write it like this. Radius 1, angle of 40 degrees. And now we want to convert that in terms of x and y, like that, what we're usually used to. And just like before, we have a triangle here. We can say that sine of theta, by definition, is equal to the opposite side over the hypotenuse. In this case, our hypotenuse is r. And the cosine of theta is going to be equal to the adjacent side, x, divided by the hypotenuse, which is r. And in this case, since we're looking for y and for x, we're going to solve these two equations for y and for x. So the first equation becomes y is equal to the hypotenuse r times the sine of theta, and x is going to be equal to r times the cosine of theta. All right, and now all we have to do is plug in what those are. In this case, r was 1. And we multiply that times the sine of 40 degrees. And here, this is 1 times the cosine of 40 degrees. Now, we need a calculator for that. So 40, take the sine. That would be 0.643. So that would be 0.643. And then here, when we take the cosine of 40 cosine is 0.766, 0.766. And then we can take those values and plug it in here. So we can say that in the Cartesian or rectangular coordinate system, the values would be, for x, make sure I get the right one, x is right here. So it would be 0.766, comma, and for the y value, I will get 0.643. And that's how we convert from the polar to the rectangular coordinate system. Now you may say, well, how do we convert back the other way? Well, again, let's say that x and y were known and you don't know what r is. Then you take this equation and simply solve it for r. So in this case, we'd say, all right, r is equal to y divided by the sine of theta. That is if y is known and the angle is known. And I can say that r is equal to x over the cosine of theta. I said, well, what if we don't know yet what the angle is? Because sometimes you only get x and y and the angle is not known. Then you first have to find the angle. And then, of course, you have to go to your tangent or inverse tangent function. So let me grab a small little piece of the board here. We can say that the tangent, by definition, is equal to the opposite, which is y, over the adjacent, which is x. Oop, and I forgot my angle in there. Let me squeeze that angle in there. Okay, so the tangent of theta is equal to opposite, y over adjacent x. And then, of course, if we want to find the angle, we go, the theta is equal to the arctangent or inverse tangent of y over x. So first you plug in your y and your x value of the Cartesian coordinate system. You find the angle. You can plug that in here. And then by knowing y and x, you can also find r. And that's how we convert back and forth between the polar and the rectangular coordinate system.